What I'm going to talk about are some results related to a study I did looking at the effects of fossil fuel soot, biofuel soot, and methane on climate. And so I'm going to describe, well, there are three simulations running here. One is a baseline simulation where I look at include all gases from all sources and particles from all sources. And then time-dependent simulations, well, the first one's time-dependent too, but time-dependent simulations with taking out the fossil fuel soot from all the sources, and then simulation with taking out all the fossil fuel and biofuel soot and gases from all sources, and then also doing an equilibrium climate simulation without methane. The only thing I'm going to do to describe the model is to show this one slide. I mean, there's a lot in the model that is important to discuss, but this slide shows kind of a treatment of how clouds and aerosol interactions are performed in the model. So we have multiple size distributions of aerosols represented by these little dots on the left side. And well, each of these, this is one distribution, let's say, but there are actually multiple ones of them, and they each have different composition. Clouds can actually form physically on each particle, and you'd get different cloud drop sizes. So this is the only model in the global model in the world that treats the individual production of cloud drops from aerosol particles physically, and the actual tracking of not only the cloud drops, but the tracking of the individual aerosol components in the cloud drops, and also ice crystals, and then interactions between all the aerosol particles and the clouds, liquid drops and ice crystals, and then the formation of graupel from the liquid and ice, or ice plus ice, and the coagulation. Now this is important with regard to black carbon, not only because of indirect effects, because this is treating indirect effects explicitly, and there is no other model that does this, no global model that does this. The important thing is that black carbon inclusions are tracked in the clouds as individual particles, and so you can actually get multiple black carbon inclusions, and you can count for the absorption by black carbon within cloud drops. And since this is one of the two most important effects on global warming due to black carbon, and not including the absorption of black carbon inclusions in clouds gives you a wrong result for your climate effects. So this is not saying this is the right result, but any result that doesn't include this is not right. So I'm just saying that to be controversial, but it's true. You really need to be rigorous about this otherwise you're going to get completely different answers. And that explains a lot why these answers are going to be different from what you see from other models that do not treat absorption in clouds by black carbon, by inclusion. Here's some of the emissions from fossil fuel sources and biofuel sources that are treated. And so one of the other differences you'll see is the biofuels are actually segregated by different chemicals, but aside from black carbon and organic matter. There are a lot of other chemicals in biofuels, and there are also a lot of gases that come out of biofuels, and these are all included too in this analysis. In fossil fuels, we're assuming we could put a particle trap or some other kind of control device, so we're only controlling the particles. So we're looking really at the control of fossil fuel soot and the control of biofuels, which would be to control all the biofuel gases plus the particles simultaneously. And so there are going to be different components that we treat. Now, just to give you really briefly some model comparisons with data that I'll just run really quickly. Here's precipitation with model precipitation versus data. The model here is at 20 times coarser resolution than the data, yet still does not predict a double ITCZ as in the data. And many models will predict 2 ITCZs, which this is nice that it doesn't do that. This is a comparison of cloud fraction with MODIS data. It matches pretty well. Comparison of modeled versus measured lightning in the annual average. Here's the top of the atmosphere thermal infrared radiation as a function of latitude. Here's some individual profiles of temperature and dew point paired in space, exact location of the sounding measurement, but averaged over a different month. Here's some ozone profiles compared with data. Here's the prediction of the sea ice in the Arctic and the Antarctic compared to the model as a function of time. Okay, so let's look at some of the results for controlling fossil fuel soot and biofuel soot separately. So each of these slides I'm going to show gives 2 sets of results. One is one with and without the fossil fuel soot, and one with and without fossil fuel plus biofuel soot, or taking them both out. I didn't actually just do one without biofuel soot. So you really have to look at the difference between the fossil fuel soot and the biofuel plus fossil fuel soot simulations to get the difference. Well, this just shows the reverse. What's the contribution? And by the way, I had two size distributions treated here for aerosols. One is what's called an externally mixed distribution, where we emit all the fossil fuel particle components into that size distribution, and then an internally mixed distribution where we emit all the biofuel and the biomass burning particle components and all other particle components, but the two can interact through coagulation as a function of size and growth. And so this shows where the distribution in the externally mixed or fossil fuel soot distribution of black carbon globally averaged over a 15-year simulation. And this left bottom panel shows the change in black carbon in the internally mixed distribution. The first thing you notice, although you probably can't read it, is this number is about 10 times larger than the externally mixed. The internally mixed black carbon is 10 times larger than the externally mixed. What was found here is that the internal mixing time due to black carbon is on the order of 3 hours, 3 to 4 hours. And that's consistent with some recent data by Praler's group. And if you look at internally mixed fossil fuel plus biofuel soot black carbon, there's more of that than if you just look at the fossil fuel soot, obviously. It's about twice as much. Now, and the other thing that we looked at here was what's the removal time of black carbon on a global scale, and that's on the order of 4 to 5 days. And this shows, well, the contribution to black carbon in snow in the fossil fuel plus biofuel soot case and the fossil fuel soot case alone. And so you'll get deposition to snow, and that's another effect. So some of the three major effects, or some of the major effects of black carbon are its effects on clouds, inclusions, the interstitial warming within clouds, so that's different. The interstitial warming within clouds between cloud drops is different from the warming due to the inclusions within cloud drops. They both have to be treated. And the warming due to BC and snow, and of course the BC in the atmosphere and its coating, its internal mixing over time. And then there are many feedbacks associated with all those, but those are kind of the four major effects of black carbon. So you get a lot of black carbon in snow. This reduces snow amount, and also then it reduces the albedo, because snow obviously is more reflective than ground underneath. So you get reductions in albedo, which are indicative in these slides. The aerosol optical depth changes, well, due to biofuel soot plus fossil fuel soot, you get more optical depth changes over India and China, as you expect, than elsewhere. If you just look at the fossil fuel soot, the magnitude of this plot is much lower than the magnitude of the biofuel plus fossil fuel soot case. But also the distribution is different. You get more in Europe and in North America, but also in China and India. Fossil fuel soot aerosol optical depth. The cloud absorption, which again is not treated in any other model, is shown here. This is the actual absorption optical depth in clouds. And for both the fossil fuel plus biofuel soot case and the fossil fuel soot case alone. And you'll get more absorption in the fossil plus biofuel soot case, obviously. And the cloud optical depth, total cloud optical depth, well, it's interesting. So this is treating indirect effects explicitly. And there's two things going on to affect optical depth. First, there's more particles when you have biofuel soot in particular, and that would increase the optical depth. But you also have warming of the clouds, which would decrease the optical depth. Now, it turns out when you have biofuel soot, they're more hygroscopic, and there's more particle number that you're talking about, and you increase the optical depth in general on the global average, although you get some decreases in some place. So the biofuel soot is increasing the cloud optical depth. The fossil fuel soot is decreasing the cloud optical depth, more because of the warming effect, but there are places of increase as well. So you do get opposite effects in terms of the total cloud optical depth from this model. What's the effects on surface solar radiation? Well, in the biofuel plus fossil fuel soot case, you get a huge decrease of surface solar over India. In fact, these reductions are on the order of 15 to 20 watts per meter squared. are consistent with data measured over India over the last 30 or 40 years. But you'll get less surface solar reduction. In fact, you get some increases in surface solar due to the fossil fuel soot alone. Now, this is due to a combination of changes in clouds and the changes in surface albedo as well, the amount of solar radiation. So you get both effects. Air temperatures, then, well, it's not surprisingly, you get warmer air temperatures due to both fossil fuel soot and biofuel soot, but you get greater air temperature increases due to the fossil fuel soot. It's just a more powerful warming agent because the biofuel soot has a lot of other components in it that tend to cause cooling. But when you account for the warming due to the black carbon in the clouds, in the snow, in the air, and interstitially between cloud drops, then you still get lots of warming due to the biofuel soot. But just to give you an idea, the total warming from these simulations is on the order of 0.5. I'll show you kind of a more global plot in a minute. 0.5 degrees Kelvin due to the fossil fuel soot alone here, and 0.7 degrees due to fossil plus biofuel soot. And keep in mind, there are a lot of other cooling components that would reduce this, so this is not the net effect of warming. This is just the isolated effect. But most of the temperature increases in fossil fuel plus biofuel soot is due to the fossil fuel soot. If we look at before we look at more climate effects, the health effect, here's the changes in the surface particulate matter. And of course, I'm giving you this with a grain of salt because this is not high enough resolution to really give you good health effects information, but it's only 4 by 5 degrees. But it just does give you a kind of first cut estimate. The particulate matter at the surface is a lot higher due to the biofuel plus fossil fuel soot case, obviously, but the number of deaths due to biofuel plus fossil fuel soot due to all the particulate matter is about on the order of 1.5 million per year, whereas for the fossil fuel soot, it's on the order of 200,000. So it's about 7 times higher death rates due to the biofuel plus fossil fuel soot case, but the fossil fuel soot is causing about 3 times more warming per unit emissions. So it has, okay, almost done. Here's the latitudinal variation of the warming. And I ran 2 simulations with the fossil fuel plus biofuel soot case. One was without the cloud absorption. Well, this one is with the cloud absorption as a function of latitude. And one of these here is without the cloud absorption. You can see that it makes a big difference in the result. And there's also methane is down here. The methane is, yeah, this one here. Methane has less of an effect at high latitudes because it's more globally distributed, but more of an effect at lower latitudes. And the fossil fuel soot case is still pretty high. It's more than methane's effect as well. Here's over a longer time. Here's over a 15-year simulation period. The 2 fossil fuel plus biofuel soot cases are between here and here. And I'd also have 2 fossil fuel soot cases that are between here and here. And then the methane is somewhere these 2 cases. But if I then extend it out to 20 to 100 years and compare to CO2, then you can see kind of the fossil fuel plus biofuel soot cases. Well, the fossil fuel plus biofuel soot is clearly, if this is right, the second leading cause of global warming. Even the fossil fuel soot, it's slightly more than the methane. And actually, I've since then started running a time-dependent simulation, a transient simulation with the methane, and this was the equilibrium simulation. And the transient simulations actually give you less warming due to the methane because you're not jolting the system with a huge anthropogenic ambient methane difference initially. So the methane curves are actually going to go down when you start looking at the transients instead of the equilibrium climate simulations. So here's some numbers. Don't read this now, but if you're interested in the slides, you can get these. These are what I call the surface temperature response functions per unit emissions. They're almost equivalent to a global warming potential, but I look at temperature change per unit emissions and not radiative forcing because that's what people are interested in. And this shows essentially, well, for methane, it's pretty close for the 100-year value is pretty close to what you'd call the global warming potential. But the black carbon numbers, and these are black carbon plus primary organic carbon in fossil fuel soot, within black carbon and fossil fuel soot, et cetera. Anyway, you can look at these later if you're interested. So to summarize, fossil fuel soot plus biofuel soot and gases is the second leading cause of global warming, behind CO2 and ahead of methane. Fossil fuel soot causes 3 times the warming of biofuel soot and gases, but biofuel soot and gases cause 7 times more death if these numbers are right. Net global warming is due primarily to gross warming from greenhouse gases, which are estimated here as 2 to 2.4 Kelvin, and fossil plus biofuel soot and gases of 0.4 to 0.7, offset by cooling due to non-fossil plus biofuel soot aerosol particles of 1.7 to 2.3 Kelvin. Fossil and biofuel soot gases may contribute then to 13 to 16% and 17 to 23% of the gross warming due to atmospheric pollutants. Controlling both or all 3 of these in isolation may reduce Arctic warming by 1.2, 1.7, or 1.9 degrees Kelvin respectively, although these are obviously too precise to believe those specific numbers. Control of fossil and biofuel soot gas is the fastest method of reducing Arctic ice. And given that other models do not include the processes necessary to simulate black carbon fossil fuel soot cases, we can say more work is needed, obviously, but we can't say, well, there's an uncertainty because other models give different results, because the other models do not include these processes, and so cannot be possibly giving the right results on this issue. Thank you.